welcome everybody. So we're going to have a mini course given by Blair Hernández on splash singularities for MHD. This is a course that will take 2 lectures. The first lecture is today, and the second lecture will be next Thursday at the same time. Okay, so Matt,
okay.
It's all yours.
All right, thank you. Before I begin, I should mention that all of this is joint work with Alberto Enciso and Diego Cordova. And today, just so you know, I'm only going to be using these 2 chalkboards because of the camera, unfortunately, but should be fine. So,
Matt, I think
yes?
you can...
You think I can remove this? Or what?
Or, well, it's up to you.
Is it difficult to hear me? No?
Oh, okay.
I'll keep it on, no worries. Thank you. Okay, so, yeah, so MHD splashes, that's what we're going to be talking about. And obviously, this kind of topic could get quite technical, but since today is the first lecture, I'm going to try to make it not so technical, and so there's going to be a lot of just heuristics and hand waving, and hopefully I can convince you that even though the details can be a little bit hairy, there's still some nice, somewhat non-technical picture going on behind everything that motivates all of the technical details. Something else that goes with this problem, or any splash problems in general, is whether or not you want to consider the 2D problem or the 3D problem. And it seems like most of the time when people discuss splash singularities, it's convenient to work with the 2D problem if you can, or if that's where the interesting dynamics are. But I'm going to try to make the case that for this problem, the 3D dynamics are especially interesting, and I hope by the end of the first half I'll have convinced you of that. So the first half is just mainly motivation for this type of problem, for the 3D as opposed to 2D, although the 2D problem is also very interesting. And for the second half, I'm going to discuss why, okay, first of all, dealing with the 3D problem is going to present some limitations. It's very challenging, and yet I'm going to hopefully convince you that the adapting the techniques to the 3D scenario is not hopeless. It actually can be done. So with that, I'll just begin. So the MHD equations model a plasma, and you could consider many different versions of this problem. You could say, let's assume that the plasma is viscous, or you could say it's compressible or incompressible. And in this version, we're going to discuss the incompressible ideal MHD equations, and with a free boundary, of course. So in this case, we have a set of equations in the interior in particular, and those are given by the equation for the velocity field u. So I have the time derivative of u plus u dot grad u, and then the forces on the right-hand side are the gradient of the pressure as usual. But then, unlike typical Euler, I have this b dot grad b term. So there's a magnetic field in the interior, and it's influencing the velocities. And in turn, I've also got the magnetic field equation, b. So I get the time derivative b plus u dot grad b, and that is going to be equal to b dot grad u. So there's kind of this interesting duality between the first equation and the second equation, where I've just taken u in the where u and b appear in the left-hand side and kind of switched the order on the right-hand side. So that's just kind of an interesting fact. So this obviously changes the dynamics of the Euler equations dramatically. And of course, I can't forget the divergence free conditions. So we have the divergence of u and the divergence of b are 0. So these are in the interior, but since we're dealing with a free boundary problem, there's obviously a vacuum surrounding the fluid. So let's say this is our blob of plasma here, and I've got these vector fields inside this domain omega of t, u and b. And then outside I've also got the magnetic field H. And the idea is that somehow H plays a role in the dynamics too. And you might wonder, like, how active of a role is that? Is that more of a passive unknown or something that's really driving the equation? And so you have to look at the equations in the exterior, which are just for H, and they are that the conditions that H is curl-free and that it's divergence-free. And we've all obviously got to deal with boundary conditions. So I'll just put the boundary conditions here. We've got that B dot n is 0 on the boundary. The normal component of H is also 0 on the boundary. And then there's this condition that the fluid moves with the velocity. So I'll just write the boundary of omega of t moves with u. And of course I have a condition on the pressure. And that's going to be that the pressure on the boundary is equal to, is this still visible here for everyone? Okay.
So is it
Yep.
B dot n equal to 0 and H dot n equal to 0?
That's correct, yeah.
Okay, and then just, now that I open my mouth, so this stereo condition on the magnetic field is coming, so what? Is there any physics behind that, or?
Yes, although I haven't prepared that sufficiently. But so essentially, it all just comes from the standard laws of electromagnetism, and you have to take a careful look at that. I mean, everything's going to come from some kind of
Ampere law or something.
Yeah, and you're going to do some. For example, you may be doing some line integral on a little box that encloses the surface, and play around with that.
Okay, yes.
But that's a very important thing to figure out. Yeah. And speaking of that, that enters in here as well, the boundary condition for the pressure. And there's different ways to phrase it, because if the pressure is represented by the gradient of something, there are different ways to write that. Right? I could describe the pressure in different ways. And the way that we're phrasing the problem, the boundary condition for the pressure just happens to turn out to be 1/2 the magnitude of the exterior field squared. And okay, so important, but now that it's out of the way, we can kind of talk about how these things affect the problem. So one thing that I want to point out, which is already kind of interesting, is that there's like sort of a wave equation hidden in the interior equations for u and b. And there are many ways you can derive that. One way is that you can take the time derivative of, say, the first equation, and then plug in the original first equation and the second equation, maybe do some linearizations. But I think there's also a nice way to see that wave equation structure by writing the equation in Lagrangian coordinates. And related to that is actually that this equation for B is, if you'll notice, the same as the equation for the curl of U in the case of the incompressible Euler equations. So that's just an interesting fact. So if I had omega equals del cross U, but this is only for Euler, so it wouldn't hold here. And omega obeys the B equation for the case of Euler. But of course, this is not the case for MHD. And the point is that if I tried to derive a curl equation by just taking the curl of the top equation, of course I'm going to generate some extra terms because I have this b dot grad b in the right-hand side. And so the curl equation is more complicated than the one for Euler. But it's interesting that we've already got some other unknown that evolves like Euler, like the curl appears to evolve in the Euler equations. And so like I said, I'm going to describe things in terms of Lagrangian variables, in particular so that we can see this wave equation structure. So if I define the trajectory map x of alpha t to be the solution to dx dt of alpha t equals u of x of alpha t, this defines the trajectory map. So it's like asking, what is the velocity at every point? Let's track the particle trajectories, and you can just determine those particle trajectories by imposing this restriction on x. And of course, I guess we need that x is the identity map at time 0, etc. And I'm going to use this notation, tilde, to denote any function evaluated at the point x of alpha t. Just a notation. So if I use that notation, and I just write the first equation, what I'm looking at is the time derivative of u tilde is equal to minus the gradient of the pressure tilde plus b tilde dot grad b tilde. So I haven't really done anything, I've just written tildes everywhere. But one might ask, do we have a nice form for b tilde? And the reason why you might expect that is that if you actually look at incompressible Euler, you have a nice form for the equivalent of omega tilde. And that's just going to follow from this equation. So maybe I should label that equation. Let's just say this is star. So the equivalent of star in this picture is dt of b tilde equals b tilde dot grad u tilde. And you could think of this as though, well, okay. Are people familiar with this formulation for 3D Euler? Has anyone looked at this, the evolution of the curl for 3D Euler, and seen this type of behavior? Okay, so if you haven't, a nice fact is that if you have an equation of this form, you can actually write down the solution just based on this. So it turns out that the solution to this equation is b tilde equals the initial, well, I'll write it as b of alpha at time 0 dotted into the gradient with respect to alpha of x of alpha t. So the idea is that somehow you're sort of magically able to reduce the number of unknowns in the problem. So it's converted into a problem for x. You can sort of say, let's just solve for x instead of worrying about b. And for 3D Euler, I would get instead omega of alpha 0 dotted into the gradient of x. So that's just a nice fact. And the way you can see this is true is just you differentiate it with respect to time. This obviously doesn't feel the time derivative, but this will. There's no problem to commute d by dt with gradient of alpha. And notice that if I applied gradient of alpha to this equation, I would also have d by dt of gradient with respect to alpha of x. I would pass the gradient onto this term. It would land on this, create gradient of u, and I would also have gradient of x. And I could just verify that it solves the equation for b tilde. And then if everything is smooth, it's the unique solution. So this is just an interesting fact, although it may or may not be useful depending on what you're trying to do, but at least we know that if we can solve for x, we've already got a solution for b tilde. But the point of this really is that I want to show how we can see the wave equation structure using this form for b tilde. So if I look at this and I plug in this, I actually find that this is, okay, we'll worry about the pressure term in a second. But if you check, maybe you'll just believe me, what you get over here is b of alpha 0 dot grad squared x of alpha t. So I've already got something that looks sort of wavy, right? I'm taking two derivatives in the direction of b. I mean, of course, sometimes the derivative is going to hit b, but this is the second derivative of x in the direction of b0. So maybe I could write it as d partial b0 squared x. So I'm already seeing something wavy because on here, this on the left-hand side, this is obviously d squared t of x, right? From this. So two time derivatives equated with two space derivatives. Of course, the pressure term is very important. And here's where it gets interesting with the free boundary problem. So if I look at the surface, I'm actually going to use these boundary conditions, and it's going to bring in the H field. Because notice right now, this is only differentiation in the direction of B, right? And now we're beginning to see why maybe there's a difference between the 2D picture and the 3D picture. So this is like a one-dimensional wave equation as far as we can see at this moment. I mean, there's more terms hidden in gradient of P, but we have to do some work to sort of uncover them. So how do I see H in this gradient of P? So I'm going to have to fudge the details a little bit, but if you'll just believe me, if you'll bear with me for a moment, let's use this boundary condition and cheat a little bit. So I'll write it up here because I'm about to cover it up. Right, we have this boundary condition. On the boundary, we have that P is equal to 1/2 h squared. And in particular, let's just think about the normal component of the gradient, because that's sort of where the interesting dynamics are probably going to come from, how things are accelerating off of the surface, or in what direction the surface is moving. The tangential behavior is not really playing a role. So what is the normal derivative of P if P has to be equal to this tangentially along the boundary? Well, I mean, I could just write it as dnP is dn of the harmonic extension. I'll bring out the 1/2. H squared. And this is where I'm going to cheat a little bit. Remember that H was solving this really nice elliptic problem in the exterior. And here I'm discussing the harmonic extension of H squared. So just believe me when I say that this is not invisible, it matters, but the term is going to look something like dn of H squared. Remember, because H is defined in the exterior, right? Modulo some lower order error terms, okay? But you have to compute that. We're cheating a little bit. But if you allow me to do that, to make this a gross simplification, what we have here is then the sum over I and j of ni di hj hj. And because the curl of h is 0, this is the same thing as ni dj hi hj. So because the curl is 0. And then this is n dot h dot grad h. So the upshot of this is that if we return to the original equation up there for u, we have b dot grad b, but also hidden in the pressure term is an h dot grad h. And again, I'm going to kind of fudge the details because that only has to do with the normal component as far as we can see here. And just believe me when I tell you that somewhere in here is a second derivative with respect to h, okay? So a key term in here looks like this. d squared h, let's put it in quotations because we're not being very precise right now. d squared h of x. But this can be made rigorous. It's just that it's a bit too technical. So we have two time derivatives of x, and then we have some important non-local stuff. But at the highest order, we have two derivatives with respect to h and two derivatives with respect to b. I'm going to erase these. Hopefully they're not too difficult to bring back if we need them. Okay, so what's the point of this? Well, let's look at the 3D picture first. What's happening on the surface? So let's suppose this is a little, I don't know, patch on the surface of the plasma. And what we've just observed is that the equation is to leading order governed by a wave equation with directions determined by the magnetic fields, right? Oh, and of course, remember, there's this H field outside, the B field inside, but they have well-defined limits as we go to the surface, right? So that's probably important to make sense of. But the point is that, you know, there's a jump in the direction of H when we go from the exterior. Well, there's no continuity between H and B across the boundary. But anyways, let's say this one is B, this one's H at this point. So we have these vectors here, but nothing is stopping these vectors from pointing in the same direction. So this is kind of unique, right? It's like saying that we essentially have some sort of wave equation determining the behavior, but it's possible for the directions of differentiation to point in the same direction. Okay? And this is kind of an important point. It's like if you're trying to solve a wave equation, so just forget the gradient of pressure, but if you're trying to solve a wave equation in which your directions of differentiation are not always orthogonal, you can have some degeneracies happening at points where they are collinear, people say. And essentially what happens is that when you try to close estimates, you find that you can't control the evolution perpendicular to these vectors pointing in the same direction. So what a lot of people do when they solve the free boundary problem for MHD is they just assume that everywhere on the surface the two vectors are in different directions. It's called the non-collinearity condition. And it seems like that's sort of a key point, like whether or not you have well-posedness or stability relies heavily on whether or not that condition is satisfied. But yeah, we don't know. In fact, you could imagine maybe there are certain shapes of manifolds where it's necessary that at least some point the two tangent vector fields point in the same direction. So these are all important considerations to make. On the other hand, in the 2D picture, it's very different, right? So let's just say this is the surface of the 2D thing. So because of just the symmetries you can... Oh, sorry, yes, go ahead.
I just got a bit... So what do we have to think? That this is a surface which is goes minus infinity and to infinity, or that it curves and it surrounds a...
In our case, we're going to deal with the compact, curves around and meets itself, yes.
So really the picture would be that
this is a small portion.
Would be like a sphere, no?
Yeah, or maybe even something more complicated, you know.
Sphere, and
yes.
the other would be like a curvy thing. Which
yes, and I think, and for us, that's the sort of shape that we're dealing with. Maybe we're going to do something like this as well.
And then just, what did you say before about the stability? What do you mean?
So, the point is that if you have perpendicular vectors, tangent to your surface everywhere, there's a natural, it's a normal wave equation, essentially.
But the stability means what, that the linearization is well posed, or?
Yeah, exactly. That's one thing that you could ask. And it seems like this is a big open issue.
But that's not, it's like there is not a well-established theory of that, or is there?
I think there is not, although I could be wrong. One of the caveats is that I think there's some steps in that direction, but people have focused on the compressible version of the problem. And I think that's going to be philosophically similar, but obviously very different in practice. No, but this is an important point, so thank you. Yeah, and if they point in the same direction, the estimates don't really, you don't have control in the perpendicular direction. That's the idea. But for 2D, you've already sort of imposed one dimensionality of tangent things, right? So just because h dot n is 0 and b dot n is 0, everything is always going to be collinear, right? And so it's just like a 1D wave equation. Now it's possible that you could stumble on a point where h vanishes, but you would still be okay as long as b doesn't vanish there simultaneously. It would still be a non-degenerate wave equation, one-dimensional wave equation. Of course, if both fields vanished, that would be a different story altogether. But that seems like less generic than something like this happening, I think. So if both b vanished at this point and h vanished at this point, yes, that would be degenerate enough that you could expect well-posedness to fail, or you just have no idea what's really going on. But we should at least be prepared to deal with something like this, I think, because it seems like much more believable behavior to just happen in nature, that you have tangent vector fields, and at some point they happen to point in the same direction. So, but again, in the 2D problem, this is not, you don't see anything like this because you've already imposed that the B field is in the board and the H field is in the board. Okay, so let's see. So obviously this is an important distinction between the 2D and 3D problem, and I think it's a point where maybe there's something more interesting going on in the 3D version. And so now I want to talk about another important difference between the 2D and 3D problems, but specifically for splashes. So that was just sort of for the free boundary problem in general. But for the splash, there's also some interesting subtleties going on. Okay, so again, this is just very hand-wavy heuristic things that we're going to discuss, but still I think they point out why the 2D and the 3D problems are both interesting for their own reasons. Let's just think about like a 2D splash, what it might look like. Well, okay, obviously it's important to sort of, we should give a quick word about maybe how you'd handle 2D splashes for the water wave equations, but I'm pretty sure everyone in here is very familiar with the kinds of tools that you use for 2D splashes, for say water wave. And but yeah, a key idea is that if you have a 2D problem and you have a bad domain, so a domain which intersects itself, you can apply a conformal transformation. So, for example, if I was considering this as a domain in C, in the complex numbers, I could take a branch cut here, apply, say, square root of z, and it would take it to a non-self-intersecting domain. So maybe I have like A, B, and here I have A prime, B prime. And the nice thing about conformal maps is that they preserve incompressibility. So if I had that the gradient of u was 0 in this world, then I would find that the gradient of u tilde, the equivalent thing, is 0 in this world. Okay? If I didn't have a conformal map, I could apply such a transformation and I get a different elliptic equation for the what was the incompressible thing, but it's not going to be quite as nice. So this is really convenient because you can kind of convert the problem into a very similar one, prove that you prove well-posedness in this picture, and then you convert it to well-posedness in this picture. Well, well-posedness, what I mean is you can give a solution which starts in this state and then ends in this state. Right? It's sort of like if I started in this state and I ended in this state, right? So it's moved away from the branch cut, for example. So it's no longer self-intersecting. So when I invert this transformation, I've found a case where I started this way and I ended up this way. Then I reverse time. Oh, if I'm dealing with an inviscid fluid, if it's a viscous fluid, that's a very subtle point. It's a much more challenging problem. But if I'm in the inviscid case, I know that if I can go from starting at this picture and ending at this picture, by time reversibility, I can say that a splash forms, if I take this as my initial data, I can then end in this picture. So this is a nice tool for 2D stuff. But in 3D stuff, I have far fewer conformal maps. I still have maps which could open the splash, but I'm not going to get something which is nearly as elegant as the solution for the two-dimensional problem. And it'll be much more difficult to solve. So this is worth noting. But hopefully in the second half I can kind of convince you that even without opening the splash with the conformal change of variables, we can still solve the necessary elliptic problems without too much pain. But another point I want to talk about that's different in the 2D picture versus the 3D picture is that let's imagine that a splash is beginning to form for the MHD equations. So I have this peak is going up, this one's going down. But in this problem, I now have an exterior magnetic field, right? So I have H here. And what I want to think about is the field lines of H. Okay? Remember, H satisfies H dot n as 0. So I can imagine what they're doing. Perhaps they're sort of curving in, coming out. Maybe they go off to infinity. Of course, you have to solve for H. Maybe you have another line coming in here. And what you might worry about is that as the splash is forming, I'm squishing these lines closer and closer together. And physics class teaches us that when you have field lines that are very, very dense and very, very tight and close together, there's a very strong force that's going on. So you might ask yourself, well, what's really driving the picture? Is it the case that H is driving the picture, and because the splash squishes the field lines together, the field lines push back and perhaps even prevent the splash from occurring? Or is it the case that the splash is forming and the H field is merely collapsing in between the waves? And again, this is just a very heuristic discussion. You need to actually go through the details to verify what's happening. But I'm going to argue that in the 2D picture, the H field is collapsing, and so it's not actually putting up much of a fight to prevent a splash from occurring. So one way to sort of justify this is that we can imagine a scenario in which the splash has already happened. So this is, again, not rigorous, but let's imagine a splash has already happened. And let's ask what H has to be doing in this scenario. So let's call this region I. Okay? And inside of I, splash has already happened. I'm just going to calculate, well, I'll say H is equal to grad phi. Okay? That's something that's going to solve the curl-free, divergence-free condition as long as Laplacian of phi is 0. And then I'm going to compute the gradient of phi squared dx over I. Okay? And I end up doing an integration by parts, and I find that these requirements plus the condition that h dot n is 0 imply that this is equal to 0. Okay? So you can calculate that if h is smooth, the only way you can have this picture is if h has become 0 inside. Okay? And then what you have to prove is that you can solve for h outside and make sense of this picture. Obviously, that's sort of easier said than done because, I have a cusp here. But this is just a vague heuristic as to why you might expect that it's reasonable for h to collapse as the splash is happening. Of course, what you really have to do is go back to the dynamical problem and prove that, the thing driving the acceleration is more the other terms in the system. But that's like a whole other can of worms. So, right. So, on the other hand, for the 3D picture, this doesn't seem to be happening. So I can imagine that if I have a 3D surface here, with the analogous thing happening, there's plenty of freedom for h to sort of pass through without any obstruction from the fact that the splash has happened. So it's, in principle, much, h is far less constrained, at least in this region, obviously, right? However, again, it's more interesting because notice in this argument, if h is smooth and h is 0 in here, h equals 0 at the splash point. Right? So my question is it the case whether or not h has to be 0 here? We know h has to be tangent, but a priori we don't know if h actually has to be 0 at the splash point. And another interesting thing to notice is that if h did have to be 0 at the splash point, we would have that at that point the two fields are only together pointing in one direction. One of those fields is 0. The collinear condition fails, rather the non-collinear condition fails if h has to be 0 at this point. I will only be differentiating in one direction, right? So it's interesting because in some sense you would expect that this is sort of a bad thing, right? If h is non-zero at this point. But it could actually be helping us to solve the problem if we could find such an h that does this. Otherwise we have to deal with the collinearity happening. So Yes, this is an important point. And so for the second half, well, the last quarter of the talk, I hope that I can kind of shed some light on how you might solve for H in a domain like this, because that's an important subtle point. And in fact, if you know how to solve for H, or things like H in the exterior of shapes like this, that's half the battle in solving the entire problem for proving local existence for a splash. And that's because the interior Dirichlet problem is closely related to the exterior Neumann problem. So let me get into the details a little bit. So the question is, what is H doing in this picture? Because it's not clear. And again, this is a point which is not quite as mysterious in the 2D picture. So that's why I think it's, again, worth the pain to deal with the 3D problem. Okay, so the problem is not the usual one for solving for, for solving the exterior Neumann problem, but you can use some of the same tools. So the fact that you have a self-intersecting domain does cause some really critical differences, but the idea is that you can still solve for H for, okay, let's say exterior elliptic stuff for self-intersecting domains. And although it doesn't seem like this general theory has been developed, but it's a little bit different from non-self-intersecting domain. But you're still going to use some of the same tools. So layer potential theory is kind of the right idea. Or it's one way that seems to work. So what we're going to try to do is solve this problem. Del cross H equals 0, del dot H equals 0, and the normal component of H, let's not say that it's 0. Let's say that it's G. And I'm just being a little bit careful here because if I impose too many zeros, then the only solution is that H has to be 0. Obviously, it depends on the topology, but a minor point is that what a lot of people do in order to get a non-trivial H is they say there's some energy source which is creating H. Maybe you add in another boundary down here, and I guess in physics you, you create some electric field on this boundary, and that is going to ensure that H is non-zero. Or perhaps you say that there's some H coming from infinity, and so you no longer have that H vanishes as you go to infinity. But let's just deal with solving this problem. Okay? So you can write H as gradient of phi, where we have Laplace phi equals 0 and dn phi on the boundary. This is all at the moment of splash, by the way, equals G. And the standard idea from layer potential theory is that you can write phi as the single layer potential of something. So I have the integral over the surface, omega, of 1 over x minus y, f of y, d sigma of y. So I've just stated that this works, but you actually have to check that for a self-intersecting surface, this works. Fortunately, it does. But again, you just have to calculate that some of these things work for self-intersecting surfaces, and some of them might not. But in this case, this formula still gives us a harmonic function in the exterior. Oh, I guess this is an important point, right? That this is happening in the exterior. Let's just be clear about that. So anyways, if f takes this, or if phi takes this form for some f, the problem is then to find the f, which results in this, right? So you can calculate that the normal, I'll write it as dn plus of phi is equal to 1/2 f of x plus the integral over the domain of k of x minus y dotted with n of x, f of y, d sigma of y, where k is some function x over 4 pi x cubed. And so again, you have to make sure that this limit is accurate, but the same calculations work. In particular, you just have to think of x arbitrarily close to the splash point. So if you're doing such a calculation for x not quite at the splash point, the same kind of calculations that you do for a standard surface will give you that this formula is true. Okay? And here I should say, okay, dn plus, I'm putting a normal vector field here, right? And I'm calculating the exterior normal. Okay. So I don't have as much time as I would like to explain this, but the general idea is that we still have an operator of the form 1/2 plus t star. So this is, I'll call it t star, this operator. And for a non-self-intersecting surface, what you would find is that, okay, at first you might worry because the singularity looks like it's two-dimensional, it's like 1 over x squared here. But the fact that as y goes to x, this is becoming tangential, you get an extra cancellation when you dot it with n of x, and you find that the kernel is just like 1 over x minus y. So it's actually integrating once, okay? So the idea is that you have 1/2 the identity plus something that integrates once. But what you're going to find is that we don't have that in this scenario. So this is like a key diverging point. So the reason why you don't even expect to have that anymore can be observed if let's impose some symmetry conditions. So let's say that this splash and the F and the G and everything are symmetric about this plane at x3 equals 0. Then what I'm computing is okay, if I'm symmetric, I'm dealing with, for example, H that is anti-symmetric. So H is like going like this, right? Up here and down here, something like this. H is equal to the gradient of phi, so it means that phi is even as I go across this x3 plane, x3 equals 0 plane. And so what I'm calculating at the splash point, when I calculate the normal derivative here, is the normal derivative, or the vertical derivative, of an even phi. So if phi is smooth, that's kind of a big caveat, but if phi is smooth and it's even, then the vertical derivative on the plane has to be 0. Right? So that means that the left-hand side has to be 0. But we didn't even ask ourselves what f was, right? So somehow, for a non-self-intersecting surface, you would have 1/2 the identity plus a lower order operator. But that's not possible. Well, this is again a heuristic, but it strongly suggests that somewhere hidden in this piece is something that looks like minus 1/2 the identity near the splash point. Away from the splash point, it's going to be the same business as usual. So you have to really dig into it to figure out what's going on there. But somewhere hiding in here is something that looks like minus 1/2 the identity as you get closer to the splash point. So maybe that's just a good lead-in for the lecture for next time. I would have liked to have given more explanation of that. But let's say that next time what we're going to talk about is how to sort of figure out exactly where that degeneracy is and how you can still invert the operator even though it has this degeneracy. Can we still use the same tools, or is it just completely different? And it's a mixed bag. The idea is still to sort of turn this thing into some sort of invertible piece, and lower order things that which integrate. But of course, it's a long process, but it's still intuitive. There's still some key heuristics which allow us to do it. So that's going to be the first thing that we discuss next time. Okay, so are there any questions?
Well, first, let's thank Matt. And any questions? Fun?
So just a quick preview of the next lecture. So most of the work is actually on this elliptic equation.
I think, well, maybe half of it or something like this, yeah. Well, of course, okay, major caveat is that
Okay,
for
so
our solution of the
my
problem...
question is actually, so the original problem is like an evolution equation, right?
Correct, yeah.
So, but how much
Okay.
part is the elliptic?
An important caveat is that our solution is an analytic splash. So the evolution equation is much easier to solve than for non-analytic data.
So
And because of that, it plays, like the elliptic problem is just the harder part of the problem. But it's true that, yeah, it's an evolution equation, so, you know, the time derivative is important, obviously. But for analytic data, you're almost cheating a little bit because it's a matter of counting derivatives, you know.
Because I just got in the end, I think I misunderstood the problem. So the h is not given. So
That's correct. You have to solve for the h.
so
Yeah.
and depends on time.
Right. Although, so remember that I said, in order to ensure it's non-trivial, you have to throw in some other stuff. So in general, what some people do is they say that there's some source, I don't know, let's say f of x t, which you're allowed to supply, which is generating h, right? But still you have to, like, I guess you're allowed to come up with whatever f you want, and then you have to solve for h. So I guess you could just say n dot h on this boundary equals this, but I think normally there's a slightly different boundary condition you put here. But yeah.
But it's a big, okay.
And that's and also the thing is though, I focused on the equation for h, but the catch or the interesting thing here is that the interior Dirichlet problem, which of course determines the velocity, you know, or the pressure and everything inside, is very important, and it's linked extremely closely with the exterior Neumann problem. And so by learning how to solve for h, we learn how to solve for everything difficult that's going on elliptically in the interior as well.
And just to fantasize, and then so this you have this piece of plasma which is in the outer space, where there is this magnetic field, and then the plasma is deforming the magnetic field by moving, by deforming it itself. It's also affecting the surrounding magnetic field.
Yeah, exactly.
That way, for example.
Yeah.
Okay. Thank you.
And the initial data?
We're taking analytic initial data.
But to open the splash?
Okay. Well, this is another sort of...
For next lecture.
Yeah, sure. But the idea is that we have all these other forces in the problem that we can work with. And remember that those other forces we're coming in with fairly high derivatives in our evolution equation. For water wave, it's very difficult to open the splash, with the evolution equation.
Sure.
But those equivalent forces are sort of appearing seemingly at a lower order with fewer derivatives in our setting than the B field, for example. So the idea is that if you have initial data for which the B field is very large or very eccentric in some way, which you're allowed to do, then you can force that the things are going to accelerate in opposite directions. You have extra forces that are going to create acceleration.
Okay. Any other questions? No? We thank Matt again. And the second lecture will be next Thursday.
Right.
Same time.
For water wave, it's very difficult to open the splash, with the evolution equation.
Sure.
But those equivalent forces are sort of appearing seemingly at a lower order with fewer derivatives in our setting than the B field, for example. So the idea is that if you have initial data for which the B field is very large or very eccentric in some way, which you're allowed to do, then you can force that the things are going to accelerate in opposite directions. You have extra forces that are going to create acceleration.